This is part 1 of Module 10, which is an introduction to operational amplifiers. This is what I plan to cover in this particular lecture. First, we're going to discuss the circuit model of an operational amplifier, then the characteristics of an ideal operational amplifier. Then we'll go into the analysis of operational amplifier circuits and see how op-amps can be used to develop standard operational amplifier building blocks. Okay, operational amplifiers, these are op-amps for short. These are very widely used circuit building blocks, particularly in analog applications. They are so widely used that they are usually introduced now during your very first course in circuit analysis. These are capable of performing basic arithmetic operations, and that's why it's called an operational amplifier, because of the operations that it can perform. We're going to study op-amps from a purely behavioral standpoint. We will not be concerned at this point with how op-amps are implemented. An operational amplifier has 5 terminals. There is an inverting and a non-inverting input. That's V minus and V plus respectively. You have an output, V sub O, and you have typically 2 supply voltages, a positive power supply and a negative power supply. This is the schematic symbol of your op-amp. You have a triangle. Okay, what is shown here, this is your inverting input. You have the negative sign to signify that. Your non-inverting input, you have the plus sign to signify that. This is your output. And then your 2 supply voltages, V plus and V minus. There's an implied 6 terminal, and this is your ground. This is the reference to which all of these voltages are based. This is an example of a real-world op-amp. This is the 741 op-amp. Believe it or not, this op-amp was introduced in 1968, and it is still very widely used. Maybe 20, 30 years ago, this is how it looked like. This is what you call a dual inline package, and this package is still used for prototyping purposes. But nowadays, this is more how you would see it in an actual application. This is what you call a surface mount version, and the surface mount version is very much smaller than the dual inline package version. These are the pinouts. So this op-amp has its inverting input at pin number 2, non-inverting input at pin number 3, and the output at pin number 6. Then here at 7, you have the positive supply voltage, and 4, you have the negative supply voltage. There are 2 additional inputs. These are pins 1 and 5, which are your offset null. Don't bother about them at this point. You're going to learn more about these inputs in the future. NC here stands for no connection. This is the circuit model of an operational amplifier. The output of your operational amplifier, that is V sub O, is driven by a voltage-controlled voltage source. So this is your voltage-controlled voltage source. The voltage that controls this voltage source is the voltage between your non-inverting input and your inverting input. You call that E sub D. So E sub D is V plus minus V minus. Okay. The output is this voltage source minus the voltage drop across this resistor. The voltage drop across this resistor is I out multiplied by R out. So that is this equation over here. Okay. Your output is AOLED, that's this voltage source, minus R out, I out, where ED, as I already mentioned, is the potential difference between your non-inverting and your inverting input. We sometimes refer to this as your differential input voltage. Between your inverting and non-inverting input, we have an input resistance Rin. Rin is typically very large. It is in the meg-ohm range. Rout is typically small. It is in the less than 200 ohm range. And A's of L is typically very, very large, in the range of 10 to the 4 volts per volt. Now, V's of O cannot indiscriminately become very, very large. No? There's a limit to the largest possible value of V's of O and the smallest possible value of V's of O. That limit is V min and V max. No? V's of O cannot become smaller than V min and cannot become larger than V max. V min and V max are dependent on V minus and V plus respectively. In other words, the larger the magnitude of the positive and the negative supply voltage, the larger the possible output voltage range of the output of your operational amplifier. These are what the output characteristics of your op-amp will look like. So this is a plot of the output voltage versus the differential input voltage, or V plus minus V minus. We assume that R out is negligible. No? If you will recall, we said that by KVL, here, V out is AOLED minus R out times I out. But if we assume that R out is negligible, we can just say that that is 0, and VO is equal to AOLED. No? That is the graph of this particular line. No? So let me clear my marking here. Okay. So this is the graph of this equation, no? This particular line. Okay, so the relationship is linear, but as I said, V's of O cannot go beyond a certain value which we call Vmax, so that when V's of O reaches Vmax, the value of V's of O will become practically constant, and you call this positive saturation. Now, on the other hand, V's of O cannot become smaller than a certain value Vmin, so when the voltage is the input voltage or the differential input voltage is decreased beyond this value, the voltage becomes constant at Vmin. Take note that the larger the value of AOL, the larger this value, the steeper the slope of the line. No? In other words, if I increase AOL, what's going to happen? So my curve is going to look this way, no? So this is going to be for larger AOL, no? Larger AOL. By the way, AOL is called our open loop gain. That's why the subscript's OL. As AOL approaches infinity, what will happen to this line? This line will become a vertical line. Let me show that. Okay, so that will now look this way. So this is the line AOL. Okay, is approximately equal to infinity. It is a vertical line, and if this is a vertical line, what is the value of E sub D? Notice that this particular case, E sub D, will be equal to 0. So what does this mean? If E sub D is equal to 0, no, this means that V plus will be equal to V minus. Okay. So again, no, the larger the value of A sub L, the more steep this line becomes. So this is a larger value. When it is approximately equal to infinity, this becomes a vertical line, and the value of E sub D becomes equal to 0. So let's take a look at an open loop op-amp circuit example. Later on, I'll explain why we call it open loop. So let's say we have this circuit. Okay. To the inverting input, we connect a DC source, which we call Vref. And to the non-inverting input, we connect a time-varying signal, which has this particular waveform. So this is Vref, and then V sub S has this particular waveform. Okay, what is the output going to look like? No? Let's assume that, okay, we want to plot V sub O versus T. Let's assume that this is just to simplify things. Vmax is equal to VCC and Vmin is going to be minus VCC. In other words, the output is limited by your positive supply voltage and your negative supply voltage directly. Let's also assume that R out is equal to 0. So what is the output going to be? No? So we said that your output is going to be AOL multiplied by E sub D. What will E sub D look like? E sub D is V plus minus V minus. V plus is this particular waveform. V minus is Vref. So this is what E sub D will look like. No? We subtract from the green wave a constant. So in effect, we are pulling down the green wave. So this is what will happen. The green wave has been pulled down so that at this point, okay, this is E sub D equal to 0. So our output, V sub O, is AOL E sub D. Now you will recall that AOL is very large. We said that AOL is typically about 10 to the 4. Okay, so let's assume that AOL, let's say AOL is equal to 10 to the 4. And let's also assume, okay, and let's say Vmax is equal to 10 volts. Okay, so what would be the value of ED that would cause the output to saturate at 10 volts? No? So to saturate, ED would be equal to Vmax over AOL, and this will be just 1 millivolt. In other words, when the difference between V plus and V minus under these circumstances is just 1 millivolt, already our output will saturate. And that can be a very, very small value. Okay, that can, okay, so that can be here, no? That can be here. Let's say this is 1 millivolt. At this point, notice that our output is already saturated. So since AOL is large, V sub O quickly goes into positive and negative saturation. So when you have 1 millivolts here, we will saturate here. When you have minus 1 millivolt here, we will saturate at Vmin, which is minus VCC. So this is what our output will look like. No? Again, for a very, very small change in E sub D, we already get negative saturation and positive saturation. As AOL approaches infinity, so as we make AOL larger, the plot approaches a square wave. In other words, as AOL approaches infinity, what will our plot look like? Our plot will look something like this. No? It will approach a square wave. Okay. And what is this? This is actually the circuit of a comparator, where Vref is our reference voltage. So what is this? What is the comparator function? When the input, which is applied here at the non-inverting input, when the input is greater than Vref, our output is VCC. On the other hand, when the input is less than Vref, our output is minus VCC, no? Minus VCC. So that is the function of the comparator. Let's discuss the ideal op-amp. In an ideal op-amp, we make the following assumptions. First, that Rin is equal to infinity. In other words, the resistance between your non-inverting input and your inverting input is infinite, meaning to say this is an open circuit. This is actually an open circuit. And if this is an open circuit, that would mean that I plus is equal to 0 and I minus will also be equal to 0. So that is the first assumption for an ideal op-amp. Now the second assumption we've already used, and that is R out equal to 0. Therefore, if R out is equal to 0, our output will always be equal to AOL-ED regardless of the value of our output current, regardless of our load. No? Because when will your output current increase? Your output current increase if your load resistance decreases. Okay? But if you have no output resistance here, there will be no voltage drop, no, coming from the voltage controlled voltage source. There will be no voltage drop, and V sub O will always be equal to AOL ED. Okay, and then the third assumption is that AOL is equal to infinity. If AOL is equal to infinity, then E sub D, which is V sub O over A sub L, if this is infinity, then this quotient becomes equal to 0. Or V plus is equal to V minus. So that's what I showed in this slide. This is the case where AOL is equal to infinity, E sub D is equal to 0, or V plus is equal to V minus. Okay. If V plus is equal to V minus, it appears that this terminal is shorted to this terminal. However, it is not a real short. We call it a virtual short because it is only a short in terms of the voltage between this terminal and this terminal. No? But in terms of current, it is an open circuit. It's a little enigmatic. No? It is a short with respect to voltage, but with respect to current, it's open. Now these three assumptions, R in equal to infinity, R out equal to 0, and AOL equal to infinity, will make the analysis of op-amp circuits very, very simple. And when we use these assumptions, usually there's very little loss in precision. When you study op-amps in more detail in your future courses, you're going to see that when you use these assumptions, okay, your error is often as small as less than 1%, as compared to using the real values of AOL, R out, and R in. The circuit that we showed earlier, okay, the comparator, we called it an open loop circuit. Okay, what is the problem with the op-amp? No? The problem with the op-amp is it saturates quickly. In our previous example, where we said that Vmax is equal to 10 and AOL is equal to 10 to the 4, 1 millivolt, just a 1 millivolt, 1/1000th of a volt difference between your plus and minus terminals will already cause the output to saturate. Okay. We don't want that to happen. No? So we need to devise a scheme whereby the op-amp will not immediately saturate. And what we do is we apply feedback. So feedback, in particular negative feedback, is used to help the op-amp resist saturation. So how is this done? Part of the output is fed back to the inverting input of the op-amp. Okay, we sample the output and maybe through a resistor feed the sample back to the inverting input of the op-amp. What happens when we do that? The feedback causes, because it is in the inverting input, as your output increases, the differential voltage is of the decreases. Decreases because we're adding a voltage to the inverting input, and therefore V minus will decrease. No? So the feedback causes ED to decrease as the output V sub O increases. So this will counteract the increase in V sub O. When we do this, the op-amp circuit becomes what we call a closed loop circuit. Okay. And this is used to implement linear circuit functions such as amplifiers, buffers, summing circuits, and filters. Okay. Okay, having said that, I now present a few simple steps in analyzing op-amp circuits. Okay, this is assuming that the op-amp is ideal. Okay, first, check that there is negative feedback. Check that part of the output is fed back into the inverting input of the op-amp. If there is no negative feedback, then chances are your op-amp is not going to be operating in the linear region. It's going to be operating either in positive saturation or negative saturation. This is because a very, very small differential input voltage will already cause it to saturate. So the first step is always check if there is negative feedback. If there is negative feedback, then we apply the assumptions for ideal op-amps operating in the linear region. That is a consequence of the three assumptions. R in is equal to infinity, R out is equal to 0, and AOL is equal to infinity. Because of those assumptions, V plus will be equal to V minus, and the current into your inverting and non-inverting inputs will be equal to 0. After having done that, we use the circuit analysis tools already studied in the early part of this course to determine the desired quantities. Usually, what is asked is the output voltage. Okay. So, an example, you use nodal analysis. Okay. Now, after determining the desired quantity, check for saturation. You still have to check for saturation. Okay. And if you see that the output is saturated, then you just have to adjust the output accordingly and recompute the desired quantities. So let's go for a few examples. Okay. So this is the simplest possible op-amp circuit, and we call this a voltage follower or buffer. So you're asked to derive an expression for the output voltage in terms of the input voltage and the circuit resistances. Assume that the op-amp is ideal. Okay, so first of all, let's check. Is there negative feedback? Yes, there is. This is my output. I sample it using a resistor and feed that back into my inverting input. So that is negative feedback. Okay. So what happens? No? As this output is increasing, okay, the differential input will be decreasing, no? Because I am making this more positive. No? Therefore, V sub I minus V minus will become smaller. And that will reach an equilibrium where hopefully V sub O will not saturate. Okay. Okay, so that is the first thing that we check, that there is negative feedback. Okay, having checked that, we now apply the assumptions for an ideal op-amp. So we said that first, V plus is equal to V minus. So V plus, let me use black. So V plus is equal to V minus. Note that V plus is equal to V sub I. Okay. Therefore, V minus will be equal to V sub I. No? The voltage at this point, V minus is equal to V sub I. So that's a result of there being a virtual short between your non-inverting and your inverting input. Okay, what is the next assumption? Next assumption is I plus is equal to I minus, which is equal to 0. So this current, I minus, is equal to 0. If this current is equal to 0, then there is no voltage drop across your resistor R. No? If I minus is equal to 0, then V of R will be equal to 0. Therefore, what does that mean? No? If there's no voltage drop across this resistor, then this voltage will be equal to this voltage. No? Therefore, V of O will be equal to V minus, which is equal to V of I. And that's why you call it a voltage follower. The output voltage, this V of O, will just be equal to this input voltage. V of O is equal to V of I. Okay, so you're saying, what is the usefulness of this circuit if my output is equal to my input? Well, the usefulness is this. Okay, if I have a source connected here, let's say this is my source, and I have a source resistance here. Okay. Remember that I plus is equal to 0. No? I plus is equal to 0. Therefore, there will be no voltage drop across R of S. No? This is my source resistance. And you get the full value of V of S applied at your non-inverting terminal. No? Therefore, this voltage V plus, V plus, which is equal to V of I, will be equal to V of S. I will have no voltage drop here. That is because this I plus is equal to 0. And sometimes our sources have very large source resistances. For example, this might be a sensor. And that particular sensor will have a large source resistance. So that the minute this current is not equal to 0, you get a large voltage drop here, and the sensor output will not be preserved. So by using a voltage follower or buffer, we are sure that the output will be equal to V of S. Because there is no voltage drop here, this voltage is going to be V of S, this voltage is going to be V of S, no voltage drop here, this voltage will also be equal to V of S. So that is your voltage follower or your buffer. A second example. So this is a classic op-amp circuit. We call this your inverting amplifier. So the problem is derive an expression for the output voltage in terms of the input voltage and the circuit resistances. We assume that the op-amp is ideal. Okay, so what our, first of all, again, check. Is there negative feedback? Yes, there is. Again, part of the output is fed back to the input, okay, here, to the inverting input. So the feedback is negative because it is fed back to the inverting input. Of course, that is not the only thing that is fed to the inverting input. You also have the input signal fed to the inverting input through resistor R1. So we see that there's negative feedback. Okay, next we apply the assumptions for an ideal op-amp. So what is that? So first, V plus is equal to V minus. Okay. Now V plus is equal to 0. Right? V plus is equal to 0 because it is grounded. And therefore V minus will also be equal to 0. Then the other assumptions are these, that this current, I plus, is equal to 0, and here, I minus is also equal to 0. Okay. So having said that, what is the next step? The next step is we apply our known circuit analysis techniques to get a relationship between V's of O and V's of I. No? So let's do a KCL, do a nodal analysis or KCL at your inverting terminal. Okay, so let's do this step by step. No? So you have V minus V's of I over R1. So that's the current flowing from right to left at R1, V minus V's of I over R1. Then you have V minus V's of O over R2 over R2. That's the current flowing this way from left to right here at R2. Okay, plus I minus is equal to 0. No? Note that there are three things connected to this node. You have R1, you have R2, and you have the op amp. But we already know that this is 0. I also know that V minus is 0. Okay, so what do I have? No? I have, okay, let me transpose V's of O to the other side. Okay, I have minus Vi over R1 is equal to VO over R2. Or V's of O is equal to negative R2 over R1 multiplied by V's of I. Okay, you call it an inverting amplifier because your output is the negative of your input multiplied by a constant. And that constant is R2 over R1. So, okay. So when you see this particular op-amp configuration, you can already tell that this is an inverting amplifier and that the gain, R2 over R1, so minus R2 over R1, you call this the gain. Okay. The gain is negative R2 over R1. So if, assuming that the transistor that does not saturate, if Vi is equal to 1, V's of O is equal to negative R2 over R1 times 1. Some very simple. Okay. Okay, so this is an inverting amplifier. What is our gain? Okay. From here, we said that the gain is negative R2 over R1 times V's of I. No? So V's of O is minus R2 over R1 V's of I. So in this particular case, R2 is 4, R1 is 1. So this is just going to be minus 4 V's of I. Now we add a constraint. Again, to simplify matters, let's just assume that Vmax is V plus, which is 12 volts, and Vmin is V minus, which is minus 12 volts. So let's fill out this table. So if your input is 1, what should your output be? No? Minus 4 times 1, or minus 4 volts. Okay, if your input is 2, okay, Vi equal to 2, what will your output be? It will be minus 8 volts. Okay, if your input is 4, okay, minus 4 times 4, so you're first going to answer minus 16 volts. But wait a minute. No? Minus 16 volts is greater than Vmax. So we know that this is wrong. No? We know that this is wrong. In other words, when Vi is equal to 4, our output is already saturated. So here, this is positive, this is negative saturation. And what should your output be? Your output should not be smaller than Vmin, and therefore my answer should be here minus 12 volts. So this is what I meant in that step. Check for saturation. Check for saturation. Okay. So when your input is 1 volt or 2 volt, that does not cause your op amp to saturate. But when your input is 4 volts, okay, then that causes your op amp to saturate. In fact, your op amp will saturate when your input is 3 volts. No? It will start saturating when your input is 3 volts because 3 times 4 is 12, which is exactly the value of, minus 3 times 4 is 12, which is exactly the value of Vmin. So you have the same situation for the next 3 voltages. No? Here you should get 4 volts. Here you should get 8 volts. Here again, this is positive saturation. Okay. So the answer is not going to be 16 volts, but the answer is going to be 12 volts. So I hope that is clear. So this is what I meant by that step, check for saturation. Okay, this is the fourth standard op-amp building block, and you call this the non-inverting amplifier. Again, the problem is derive an expression for the output voltage in terms of the input voltage and the circuit resistances. Okay, again, first check if there is negative feedback, and in this particular case, yes. V sub O fed back to the inverting input, okay, through resistor R2. Okay. So what is the next step? No? The next step is we apply the assumptions for your ideal op amp. So V minus is equal to V plus, but V plus is equal to VI. No? Therefore, V minus is equal to VI. So this is V minus. Okay. And then we apply I plus is equal to 0 here, and here I minus is equal to 0. Okay, next, what can we do? We need a relationship between VO and V sub I, so we can apply KCL at the inverting input. Okay, so what is that? You have V minus over R1. Okay, that's the current going from right to left here. Then you have V minus minus V sub O over R2. Okay. Plus I minus is equal to 0. No? Again, we know that I minus is equal to 0. And we know that V minus is equal to V sub I. Okay, so simplifying, I get V sub I 1 over R1 plus 1 over R2, okay, is equal to V sub O over R2. Okay. If I multiply both sides of the equation by R2, okay, I'm going to get now V sub O is equal to 1 plus R2 over R1 multiplied by V sub I. So my gain is equal to 1 plus R2 over R1. Notice that I could have gotten exactly the same expression by applying voltage divider to this particular path. No? Because since I minus is equal to 0, then V minus can be expressed in terms of V sub O by the voltage divider equation. You have V minus, okay, yeah, we can do that, ano? Alternative solution, okay, by voltage divider, okay, V minus is equal to V sub O R1 over R1 plus R2. Okay, which is equal to V sub I, because V minus is equal to V sub I. So you just have V sub O is equal to R1 plus R2 over R1 V sub I, which is exactly what we have here, no? 1 plus R2 over R1 V sub I. So it's the same. This is the same as this. Okay. So that is your non-inverting input. Okay, just some things that you can observe. Okay. First of all, the gain, the minimum gain is equal to 1. We cannot have a gain that is smaller than 1. So this occurs when R2 is equal to 0. So if I short this resistor, R2 is equal to 0, automatically my gain becomes equal to 1. No? That also occurs, no, when R1 is equal to infinity. Okay, if R1 is equal to infinity, this becomes 0, and my gain is equal to 1. In other words, if this is an open circuit, then V sub O is just equal to V sub I. And you will note that if R1 is equal to infinity, then the circuit is just a buffer, which is our first example, a voltage follower or a buffer. So take a look at the first example that we had. Where is that? This one. No? So this is the case when the resistor that connects this to ground is equal to infinity. Okay. Okay, the last circuit that I want to show you is this. This is a current to voltage converter. And this is very easy to analyze. Okay. Again, V plus, first of all, you see the presence of the negative feedback through RF, the feedback resistor. So if there is negative feedback, then there's a good chance that this is not going to be saturated. Let's assume that the output is not going to saturate in this particular case. Then we have V minus is equal to V plus, assuming that the op-amp is ideal, which will be equal to 0 because V plus is equal to 0. So V minus is equal to 0. Okay? Okay, applying KCL to this particular node, okay, what do I have? If I apply KCL to that node, okay, we apply KCL to the inverting input. Okay, I have I in or negative I in because it is going toward the node, plus V minus V sub O over RF, although we already know that this is 0, no? V minus is equal to 0. Okay, plus I minus is equal to 0. Again, we already know that this is 0 because of your because this is an ideal op amp, no? I minus is equal to 0. Okay, so what is V sub O? Okay, V sub O is just now going to be negative I in multiplied by R sub F. It is a current to voltage converter. It converts this particular current to a voltage. No? The voltage, the output voltage is proportional to the input current, although there is some inversion, no? Because of this negative sign. So VO is equal to negative I in times R sub F. Okay, that's the last example that I have for this part 1. What did we achieve in this lecture? Okay, after you've heard and tried to understand further this lecture, you should now be familiar with the circuit model and the output characteristics of an op-amp. You should know the characteristics of an ideal op-amp, and you should be able to analyze basic op-amp circuits. Furthermore, you should now know what the topology of an inverting amplifier is, a non-inverting amplifier is, and a buffer and a current to voltage converter. So that's it for part 1. Part 2 to follow.